in Taiwan. And the first time I met him was in a JSON conference, and because I was working with my advisor, Dr. Yen-Tsung, and we are working on statistical genetics, and Dr. Huang is more involved in like mediation analysis, and like so basically this is a very hard area. And also my student and my collaborator who is working on Alzheimer's disease is very enthusiastic to learn more about the mediation analysis in like a time to event data setting. So that's why I invited Dr. Huang to give a talk for this area and this subject. So let us welcome Dr. Huang for today's speak. Thank you.
Okay, thank you. Can you hear me well?
Yes.
Okay. So first, I would like to thank Dr. Chen for the invitation and the kind introduction. It's my great pleasure to share my work from the other side of the earth for most of you. So today I'm going to talk about a non-parametric causal mediation in a time to event setting. This is probably not directly related to statistical genetics, but I think it's still a very important topic in causal mediation. Okay. So this is a joint work with my former assistant, Jason, who is currently now a PhD student at UC Davis. So about this talk, briefly, this is about causal inference, causal mediation, and mostly in time to event setting. So it's more about the survival analysis framework. So first, I would like to share my perspective of data science. So I think, if we work on data science, and usually it's very important to formulate your scientific hypothesis, and then from your scientific hypothesis, you come up with an estimate. Okay, so estimate can be like something like just a parameter, or could be a function or even functional. And then we try to achieve some estimate. So from scientific hypothesis to estimate, this is where we need causal inference. And from estimate to achieve a good estimate, this is where we need statistical inference. So I'm going to split my talk into causal inference and statistical inference. And so let me start with the introduction. I will introduce our motivating example, which is about a natural history of viral hepatitis. And I will briefly talk about my recent work where I propose non-parametric causal mediation analysis for semicompeting risks. And in the invited discussion for this paper, some issues came out, and especially for causal assumption, and which happened to be at least partly addressed by a parallel project that I'm going to talk about today. So the scientific of interest here is that we are interested in the natural history of viral hepatitis. For example, if patients were infected by hepatitis B, their liver will have chronic inflammation and fibrosis, where when there is a massive amount of fibrosis, it will become liver cirrhosis. And during the repeated inflammation and recovery, liver cells may accumulate somatic mutations and become cancer cells. Eventually, patient will die. Okay. So what we are interested here is 3 milestone events: hepatitis, liver cancer, HCCs, liver cancer, and death. The data, the motivating data is a cohort study conducted in Taiwan by Professor Chen Jianren. They recruited about 23,000 participants during 91 and 92 and follow them prospectively. So it's more than 25 years of follow-up. And then we link this cohort to a large nationwide database to determine their disease instance and mortality. So if we look at this illustration, that at the study entry, the cohort measured their hepatitis infection status. And during the follow-up, the more than 25 years of follow-up, we link to the National Health Insurance Research Database to determine the occurrence of diseases and mortality. And this analysis is subject to semicompeting risk, which is a classic problem in biostatistics. It was first described by Yen-Tsung Huang as a phenomenon that the intermediate event is subject to censoring by a terminal event, but not vice versa. For example, a patient who dies is no longer at risk for cancer, but a patient with cancer is still at risk for mortality. So the competing mechanism is one directional. Okay. And there has been two main approaches to semicompeting risk. One focuses on the joint survival function of the two events, for example, using a cobular model. And another approach classifies the patients into three states: healthy, diseased, and dead. And this approach focuses on the transition probabilities between different states. And here, we would like to propose yet another approach using causal mediation modeling. So causal mediation model decompose the effect of hepatitis on mortality into a blue direct effect. So this is the effect not through liver cancer, and the red effect that is through liver cancer. And mediation analysis actually was first proposed in social science literature, and there has been a lot of development recently. Okay. So in a recent paper, I proposed a non-parametric estimator for causal mediation, where we are able to identify direct and indirect effects by discounting process-based formulas. We also established their asymptotic properties using martingale. And like most of causal analysis, our method depends on strong identifiability assumptions. In the invited discussion for the paper, some experts in causal inference raised the following issues. So first, I'll propose effect are so-called natural direct and indirect effect, which are commonly studied but may have difficulties in interpretation. Therefore, they advocate another approach, which is also just published in this year in JASA, termed separable effects. I will talk about that in the end if we have time for discussion. And the second issue is that our proposed method depends on a cross-world independence assumptions, like this notation. I'll explain in the next slides. Okay. So the cross-world independence assumption is like, let's first imagine a universe, okay? And then there are two other parallel universes. So in this parallel universe, everyone received hepatitis status as Z prime, okay? Therefore, we observe a random variable M of Z prime, okay? So that's for this universe. And in another parallel universe, everyone received a joint intervention Z and M, and we observe a random variable for the outcome Y of Z and M, okay? The cross-world independence assumption is saying that these two random variables, M of Z prime and Y of Z and M, they are independent. So it is, more like a conceptual assumption, because we don't really get to observe two parallel universes, and then we don't have the probability distribution for those random variables. But the identifiability that we try to achieve in our method require this kind of assumption. So if we put this notations in words, so Y of Z M is the mortality occurrence with hepatitis cancer being set to little z and little m. And m of z prime is a cancer occurrence with hepatitis being set to z prime. Okay. And if there exists something like X, and then X have this structure, and for example, X could be a liver cirrhosis. So hepatitis can affect liver cirrhosis, and liver cirrhosis can affect M, that is liver cancer, and liver cirrhosis can lead to mortality. Okay. And if this structure exists, and it will violate this closed world independence assumption. So let me briefly explain using the non-parametric structure equation model. Okay, so let's think about all the random variables as a non-parametric function. Okay, and the input are the variables that have arrow into this variable. For example, y of z and m is that we have input of z, input of m. We also have an input from x, and x itself is another function because it's the random variable, and also its own arrow term epsilon y. Okay, and then m of z prime can also be expressed as a function. So they have an input of z prime and x and epsilon m. Okay, and again, x itself is another function. And because these two notation, they share the function of x, and then even though they have different input z and z prime, but they share the same epsilon x. So these two random variables, they are not independent because of the sharing of the epsilon x. So that's the simple explanation why, if there exists the x and this structure, they will violate this cross-world independence assumption. So if we go back to our natural history of viral hepatitis, X, can be a liver cirrhosis, okay? And it affects liver cancer and mortality, and it is also, affected by viral hepatitis, okay? So in the following work, I'm going to incorporate the liver cirrhosis as an additional mediator. And so, our model will become a multivariate version of the semicompeting risks. Okay, so I think I will spend most of the time talking about causal inference. I'm not sure how much time left for statistical inference, but if I can cover causal inference, I think I will be happy for today's talk. Okay. So in order to get around the cross-world independence assumption, we adopt the so-called interventional approach, okay? And this is also a new concept in causal inference. I'm going to explain in the following cartoons. So this is a directly acyclic graph or DAG that we would like to study. And Z is the hepatitis status, and N1 is the status of liver cirrhosis, N2 is the status of liver cancer, and N3 is the mortality status. So first, let me explain this notation, N1 star of ZD. So let's intervene everyone to have status ZD, okay? And then follow them, and we observe an outcome N1 of ZD, okay? So that's N1 of ZD. And the N1 star, so N1 of ZD will have, it is a random variable, okay? And then it has a probability distribution, and N1 star is a random draw from this distribution. So in other words, N1 star and N1, they share the same distribution, okay? And similarly for N1 star of Z, C, okay? So this is something slightly more complicated. Okay, so this time we intervene everyone to have ZB, and then we intervene their N1 status randomly from a random draw of N1 star of ZC. And from this joint intervention, we observe a counterfactual outcome N2 of ZB and 1 star of ZC. Okay. And the N2 star, again, it is a random draw from the distribution of N2 of ZB and 1 star of ZC. Okay. And finally, this is something slightly more complicated. So this time we have triple interventions. we have intervention of ZA, we have intervention of N1 star of ZD, and the intervention of N2 star. Okay, and from this triple intervention, and then we observe this very complicated counterfactual outcome. Okay, which I'm not going to spell it. So under the interventional approach, the identifiability assumption is just simply the conventional sequential ignorability assumption. Okay, or equivalently, you can view this assumption as a no confounding among the relationship of Z, N1, and N2, and N3. Okay. So far, we just explained the notation. Okay, so next we would like to use those notations to define the interventional version of the path-specific effect. So what is path-specific effect? That is, I would like to define a causal effects in every possible path in the causal diagram that I just showed you a few slides ago using interventional approach. Okay, so first let me explain this this effect. Okay, so this is the notation that I just explained, and then subtracted by the notation under different ZA intervention. One is under ZA1, the other one is under ZA0. Okay, so this is not a very accurate notation. You know, I should put an expectation or some probability statement, but here I just make it simple. I just want to contrast some probability measure about these two random variables. Okay. So again, I would like to build the intuition using a diagram. Let's try to look at these two diagrams and to see what's going on for this subtraction. Okay, so the arrows with the same intervention like ZB, ZC, ZD, they will cancel each other. Okay, so therefore, what we are really contrasting are the ZA1 and ZA0. Okay, and then ZA1, you know, is for this arrow, and ZA0 is for this arrow. So what if we take a difference between these two? What we really get is the effect embedded in this arrow. Okay, so this is the path the effect from this path that we obtain from this calculation. Let's compare the intervention of ZB1 and ZB0. Okay, so this time, so again, so we have ZA, ZB, ZC, and ZD, and the ZA with the red color, ZB with the blue color, ZC with the orange color, and ZD with this purple color. Okay, so if they have the same status like ZA, ZC, and ZD in this example, they're going to cancel each other. So what we have here is the contrast for this this blue arrow. Okay, but remember, you know, this notation. How can we obtain this notation? You know, we explained this. Actually, this notation for this ZB1 and ZB0, this is the effect from this arrow. Okay, so from the previous round of experiment. So if we are really taking the difference between these two, to be fair, we are actually comparing the effect from this entire path. Okay, so this is another path-specific effect. That's another example. So ZC1 and ZC0. Okay, so again, ZA, ZB, and ZD, they're going to cancel each other. So we are contrasting this orange arrow. But again, this notation, you know, we you know, have this effect from this this orange arrow, and for this notation, actually, this is the effect from the previous arrow. So in the end, what we are really estimating is the effect from this entire horizontal path. Okay, from Z to N1 to N2 and then to N3. So this, I'm going to skip this one. Okay, so if you take a difference between ZD1 and ZD0, you will obtain this path. So here in total, we have 4 possible paths And using this notation, the interventional framework, we are able to identify all possible path-specific effects. Okay, so far I use graphs to help visualize the four path-specific effects. And next, I would like to provide a more formal definitions with notations. Before I do that, let me start with the random variables of interest. Okay, so here we have T3 is time to death, and T2 is time to liver cancer, and T1 is time to liver cirrhosis. C is censoring time, and Z is the hepatitis status. With those random variables, we can further define a few processes. So N3 tilde is the event process of mortality, and N2 tilde is the event process for liver cancer, and N1 tilde is the event process for liver cirrhosis. And N3 without tilde is the observed process for mortality, and similarly for N2 and N1. So, with the tilde is the underlying process, and without tilde is the observed version. Sorry. And Y is the at-risk process of mortality, and 1 represent the subject still at risk for mortality. Okay. And for the at-risk and the event process of mortality, Y and N3, we further define a new conditional process. It is the process conditional on the liver cancer and the liver cirrhosis status, N1 and N2. Okay. And similarly for the at-risk process. Okay. And because we are doing causal inference, so we also need to define a counterfactual outcomes. Most of the causal inference define counterfactual quantities on random variables. Here we define a counterfactual on the processes. Okay, so that's the main difference of our approach. Okay, so the N3 tilde is the counterfactual process of death. Okay, and N2 is a counterfactual process of liver cancer, and N1 is a counterfactual process for liver cirrhosis. Okay, and they have their corresponding intervention from a previous event. And this is our key estimate, okay? So estimate is the statistical quantities that we would like to estimate in order to address a scientific question. So here our estimate is a counterfactual hazard function. Okay, it is a conditional probability and it is a probability of death at time t conditional on being alive at time right before t. So it actually follows the same definition of conventional hazard, except here the process is using the counterfactual process instead of the conventional process. Okay. So this counterfactual process of that involve 3 interventions: Z, N1, and N2. Okay, and the N1 itself is a counterfactual. It's a counterfactual outcome. It's a counterfactual process. Okay, and the N2 is another counterfactual that receive intervention of yet another counterfactual. Sorry. And those different counterfactual, they are under different intervention of Z. Okay, so here we have ZA, ZB, ZC, and ZD, as we showed in the causal diagram earlier. Okay, so here we just put everything into a formal notation. Okay, so based on the causal assumptions, we are able to move from the definition of the counterfactual hazard to this expression. And this expression actually involve the 3 conditional probabilities. Okay, so D lambda subscript N1, N2, and the W N2's conditional N1 and the W N1. Okay, so those actually are conditional probabilities. And what we would like to do in the statistical inference is to propose non-parametric estimators for those 3 conditional probabilities. But before I do that, so let me again look at the diagram. So the path-specific effect of Z to Y is this red path, and the path-specific effect mediated only through N2 is this blue path, and the effect mediated through N1 and then to N2 is this orange path, and mediated only by N1 is this purple path. Okay, so plugging in different configuration of ZA, ZB up to ZD, we can identify all possible paths as we show in the previous animations. Okay, so far we formulate our scientific question of hepatitis natural history as a causal mediation problem. And then we define path-specific effect on the diagram and provide formal definition using counterfactual counting process. And finally, we define our key estimate, the counterfactual hazard lambda, as a joint intervention of ZA up to ZD. Okay, so this is causal inference, and then the remaining work is to propose a good estimator for our estimate lambda. Okay. Okay. I think I'm gonna skip this part. Here, I just try to explain. If we have time, we can go back. We just try to explain why the interventional approach can get around the problem of the crossword independence assumption. Okay, I'm gonna skip this part. Go to the statistical inference. Okay, so far we have covered causal inference, and next let's talk about statistical inference. So we need a couple of statistical assumptions, and most of them are very standard in survival analysis or competing risks analysis, semicompeting risks analysis, like independent censoring, and then later event will censor the former event, those kind of traditional assumptions. One special assumption is this part. Okay, so this is the so-called Markov assumption. So this assumption says that if you are alive at time right before T, the probability of death at the next moment only depends on the status of disease at time right before T, not the entire disease history. So in other words, if a patient A had a cancer 10 years ago, and the patient B had a cancer yesterday, their probability of mortality is the same, given that they are both alive until now. Okay, so that's the Markov assumption. It's a strong assumption, but we needed to establish the martingale property. So this is our estimator of the counterfactual hazard. And it is a non-parametric estimator. It involves three key estimators for WN2 conditional N1 and WN1, and then D lambda N1 and 2. They can be explicitly expressed by the risk and the event process of mortality that we introduced earlier. And we would like to emphasize that the process Y and N3 are defined conditional on the disease status N1 and N2. Okay, and in our previous work, in a single mediator setting, they share a very similar structure with the weighted scheme. W and status depends on hazard, and what we obtain here is, you can view it as a generalized version of this estimator. Okay, so I think I'll skip this part as well. Okay, so here is our estimator, but that's take a closer look. So if you're familiar with survival analysis, you may easily recognize that this part is actually the Nielsen-Allen estimator. Okay, so in a denominator is how many of the subjects still at risk, and then in the numerator is how many of them have the event. at time t, at time s, okay? But here we have a subscript N1, N2 that indicate the status of liver cancer and liver cirrhosis. So you can view, this Nielsen-Allen estimator, you know, as a status-dependent Nielsen-Allen estimator, okay? And we also have a time-vary weighting scheme, okay? So this Nielsen-Allen estimator, you know, they have to be weighted by different time, okay? But by the prevalence of a disease at different time, okay? So if I may, our estimator can be viewed as a status-dependent Nielsen-Allen estimator with a time-vary weight for the intermediate events, okay? So I use this illustration to hopefully build a better intuition about our proposed estimate. So here, each line indicates the follow-up time for each individual, and the cross sign indicates death, and different colors of line represent different disease status. So the green color indicate the subject is free of liver cirrhosis or liver cancer. The purple color indicates that the subject developed liver cancer. The gray color indicates the subject developed liver cancer. Sorry, the purple color is developed liver cirrhosis, and gray color indicates the development of liver cancer, and black color indicates the subject developed both. So our estimator is first decomposes the follow-up time into different colors. Okay, so different status of the diseases. So within the same color, we estimate the hazard of mortality non-parametrically using Nielsen-Allen estimator. Okay, and then combine them, combine different hazard under different disease status by taking the weighted sum. Okay, and then the weight, is coming from the prevalence of different disease, you know, the combination of different disease status. And then we plug in different configuration of Z's, and then take the difference on the different configuration of Z's to contrast the 4 past-specific effects. Okay. So here, this is very similar to what we saw previously, except here we plug in our estimators, so they have the head. Okay, so here is the estimator for the counterfactual hazard, and then we take the difference under 1000, so only ZA is equal to 1, and subtracted by the counterfactual hazard under all Z's to be 0. So this is the first past-specific effect, and similarly for the other 3 past-specific effects. Okay. So okay, I can explain this. The important part of our proposed estimator depends on this new process Y. Okay, so this is the at-risk process. So in a conventional survival analysis, the at-risk process is like this. Okay, so you are at risk, and then you jump to 0 if you are no longer at risk, and you know it could be you die or you drop out of the study. Okay, but what we define here is, okay, I want this at-risk process to depend on the other 2 stochastic process, one for liver cirrhosis, the other one for liver cancer. For example, if this is the process for N1 and N2. So our proposed conditional at-risk process have 4 different possibilities: 1, 1, 1, 0, 0, 1, and 0, 0. Okay. So for 1, 1, it is only jump to 1 at this small interval because you have to be at risk, and then your N1, N2 has to be 1 at the same time. So only this small interval satisfy this condition. Okay. And for 1, 0 is this interval because you have to be at risk, and then your N1 has to be 1 and your N2 has to be 0. And for 0, 1, there's no interval satisfy this criteria. And for 0, 0, you have to be at risk, and then your N1 and N2 has to be 0. So it's this part. So basically, what we define here is to take the original at-risk process, okay, and then decompose this process into 4 different components, depending on the N1 and N2 process. So this is what we are doing here. Okay, and similarly for the event process. Okay, so this is the event process for the conventional survival analysis, but now we chop that into 4 different pieces, depending on the N1 and N2 process. Okay, so that's what we are doing. And using this newly defined at-risk and the event process. Sorry, I'm gonna skip these cartoons. We obtain this technical results, and which is very important, you know, for us to develop the following theoretical properties for our estimators. So in our newly defined event process, if we subtract it by its compensator, we define our compensator using our newly defined risk process and also the lambda that we need in our estimation of counterfactual hazard. So taking the difference between this event process and this compensator, under this filtration, we are able to establish that the difference here is a zero mean martingale. Okay, and using this, we can easily establish the following results. So we show that our proposed estimator for counterfactual hazard is asymptotically unbiased, and then we also achieve uniform consistency and such that we have a uniform consistency for the 4 path-specific effects that we are interested in. Okay. And we also established the weak convergence. Okay. So this is a key decomposition. So we are able to decompose our decompose this into the these 2 components. And for the first part, we can use martingale to establish you know, this part will converge to a Gaussian process. And for the second part, we can use the empirical process to establish another Gaussian process. And we can show that these 2 parts, they are asymptotically independent. So it becomes a summation of 2 Gaussian processes. Okay, so eventually we can also show that the 4 path-specific effects scaled by the square root of sample size, they all converge weakly to Gaussian processes. So like most of the studies, the simulation looks good, and then they have a proper coverage. So yeah, we can look at the analysis. So finally, we apply our proposed estimator to the cohort study that I just introduced in the very first beginning. And then we estimate the 4 path-specific effects. Okay, to remind you here, Z is the hepatitis B status, and N1 is liver cirrhosis, N2 is liver cancer, and Y is mortality. Okay, so the red curve stands for this effect. That is the effect not through liver cirrhosis or cancer. So it turns out it is not significant. So in other words, most of the effect of hepatitis B on mortality is through either cirrhosis or cancer. And here we see that if it's mediated only through liver cirrhosis, is this purple curve. If it's only mediated by liver cancer, is this blue curve. And if it's mediated by both cirrhosis and liver cancer, is this orange curve. Okay. So that is for hepatitis B. Okay. For hepatitis C, they have slightly different pattern. The major difference is the red curve. So the effect of hepatitis C on mortality, not through liver cirrhosis or cancer, actually it is significant. Okay, and the effect size actually is quite large. Okay, and they also have a significant effect for the effect mediated by cirrhosis, by cancer, or by both. Okay, and we can further calculate their relative contribution. So the effect mediated by liver cirrhosis is about 19%, mediated by both is about 13%, mediated only by liver cancer is 23%. And interestingly, not mediated either by liver cirrhosis or cancer is actually quite large. It's almost 50%. Okay, so that indicates that hepatitis C, they can lead to mortality through diseases, through non-liver diseases. Okay, and they also, compatible with clinical literature, where it is quite well known that hepatitis C is a systematic disease. So they have intrahepatic component as well as extrahepatic component. So the proportion actually is by this formula. So we define a total effect as an effect of a summation of the 4 pairs-specific effects. And the proportion for Z to Y, it is you take this pairs-specific effect divided by the total effect. But we also take the integral from 0 to a certain time point t. And similarly for the other 3 pairs-specific effects. Okay, so in summary, here we show that disease natural history can be conceptualized as a causal mediation model through counterfactual counting process. And the interventional approach categorizes all possible mechanisms. And we propose non-parametric estimators for interventional path-specific effects and establish their asymptotics. We show that in the analysis, both liver cancer and liver cirrhosis mediate hepatitis-induced mortality. Okay, so since we still have some time, so I want to build some connection with a recent literature in causal inference. So Stenstrad et al. Recently published a paper in JASA, and they propose a new causal effect called separable effect. Okay, so in their setting, they are not really consider a semi-competing risk problem. Instead, they consider a competing risk problem. So they are interested in the effect of Z on N1 and N2. And the competing mechanism is that N1 can compete N2 and N2 can also compete N1. So it's slightly different problem from what we are looking at here. And then they separate the effect of Z on these 2 outcomes into 2 components. So ZN1 is the effect that only affect N1. And the ZN2 is the component that only affect N2. So if you think about Z as a drug, as a small pill, it's like you can break this small pill into 2 pieces. One is only affect N1, the other one is only affect N2. Okay, and in their work, their identification involve this formula. If we write this formula in terms of Hazer, okay, so this is the Hazer conditional on the Z, is using only ZN2, and then multiplied by conditional on Z only involve ZN1, because this is the effect for N1 and this is the effect for N2. Okay, and it turns out this is very similar to our estimate. Okay, so our estimate is like this. Okay, so we also have a 2 Z component. One is ZA, the other one is ZB. Okay, and then ZA affect N2, ZB affects N1. And so it's a very interesting connection that, we don't explicitly saying that our Z can be split into two components. Instead, we say, okay, we can use different intervention to affect N2 and N1, okay? And another connection is that in our estimate, we have to sum over different possibilities of N1. So here only have two scenarios. So N1 can be either 0 or 1. Okay, so our N1 can be either 0 or 1. So 0 indicates that you don't develop the intermediate events yet. And if it's 1, that means that you already develop the intermediate events. So we sum over the two possibilities. But in the separable effect, they only consider N1 equals 0, okay? Because they concerned about the competing event. So they want to fix the other event to be, not happening yet. Okay, so that's the main difference. But here we are studying a semicompeting risk event. So we have to consider all possibilities for the N1 status. So we have to take the summation. So I feel like this is an interesting connection with other people's work. Okay, so in the end, I would like to thank the grant support from Ministry of Science and Technology in Taiwan, and also the support from Academia Sinica. And I would like to thank my PhD student Yiting for conducting those data analysis of the cohort study. And my collaborators, Professor Chen Jianren, Hua Yi, and Mei Shen, and also Dr. Yao Junxu. Thank you very much.
So I will be leading the question period. Are there some questions about this very interesting presentation? Comments? Okay, so could you come back on why do you need counterfactual in this context? Because now we have hepatitis, we have liver cancer, liver cirrhosis. So what do you capture with the counterfactual in this context?
Yeah. So the reason we need counterfactual is that we are really interested in the causal effect. So in order to formally define what causal effects are, starting from the counterfactual, we can understand the definition more rigorously, and then from a definition, we derive the expression of our estimate. Okay, so I think that's the main reason why we choose to start from the counterfactual.
So, but in the counterfactual, so what would be a person or a pseudo person in your counterfactual world? Would it be, for instance, somebody who has a hepatitis C, but no cirrhosis, no cancer, and then the person dies?
Okay, I see what you mean. Okay, that's a good question. So, it is possible that, someone will have hepatitis and then they experience a very acute liver failure. So they will, experience mortality very fast without going through, liver cirrhosis or liver cancer. So that's one possibility, if you go straight from hepatitis to mortality. And also another scenario is that, like hepatitis C, some of hepatitis C patient, they will develop kidney disease, like renal disorders. And they will go through, end-stage renal failure very fast. And so they die without experiencing, liver cirrhosis or liver cancer. So that's another possibility.
So this person would be taken out of your counterfactual world. Because I mean, you're not interested in kidney disease.
I did not formulate the kidney disease into my problem.
Okay.
Yeah. Yeah.
Okay.
Not in this study, but in other study, we do use kidney disease as one of the mediators.
Okay. Okay. So maybe Alexandre, you want to ask Alexandre? You have a question?
Yeah, thank you, Paul. I'm actually following up on this. I just want to clarify if I understand correctly. It seems to me that a person can be used to contribute to the estimation under different conditions than what he actually experienced, or different processes and what he actually experienced. Through these counterfactual, you're kind of making a person be something that it is actually not going through. And through your strong assumptions, like the Markovian assumption, you achieve to a contribution of that person to a lot of these terms, and that buys you a lot of efficiency. Is that the principle? You're making these strong assumptions to use as much as information as possible?
Thank you for your question. Let me think a little bit. I think the Markov assumption, maybe I should go back. Okay, the reason I need Markov assumption is that, say we are now working on another estimator that do not depend on Markov assumption. Okay, and there, what we need to deal with is that not just the status of the intermediate event. Okay, so because here we only concerned about at the time right before T, whether you have this disease or not. If 0 means that you don't have a disease, if 1, that means you have disease. Okay, so the Markov assumption only cares about, you have a disease, say N1 equals 1, you have a disease, but they don't care about when you have a disease. Mm-hmm. Without Markov assumption, you have to explicitly spell out, okay, your T1 equals little t1. And then you have to take the integral over all possibilities of different values of T1. And there you will have another layer of integral. So what Markov assumptions save us here is that we don't need to go through that integral. We can simply only focus on the status at this fixed time. And okay. Yeah, and then in terms of the subject may contribute to different status, right. I think, across different times, if the patient at earlier time, it is free of disease, and then it will contribute to N1 equal to 0. But later, if it becomes develop a disease, it will contribute to N1 equals 1. So depends on different time points, it will contribute to different stages. Yeah.
Okay, I think I got that. Thank you.
Thank you.
Other questions or comments? Okay. Maybe a last one. Maybe what about Sobel's test? When you do mediation analysis, I guess a standard procedure is Sobel test to test whether there is really a mediating effect. So can you carry out such tests in your models?
Yeah, that's a good question. For testing, I think the most convenient way would be just to invert your estimator, because we already showed that it converged to a Gaussian process. And then you can take the integral across the entire study period and make it a normal distribution, and then invert this estimator to perform a wall type of test. And that's the most convenient way to conduct a test. but there are actually some issues because one major challenge of mediation hypothesis test for mediation is that, if we think about just a single, say you only care about this part from Z to N1 to N2, okay? So the mediation is this Z to N1 and then N1 to N2, okay? So the null hypothesis of mediation is that, if this effect is missing or this effect is missing, they both constitute the null hypothesis. In other words, if say this is alpha, this is beta, the null hypothesis of mediation effect is not alpha and beta equal to 0. Instead, it is alpha equal to 0 or beta equal to 0. So it becomes the null hypothesis is not a single point. It is the entire, it has a very different combination. It is a composite null hypothesis. And unfortunately, we don't know the composition of different nulls. If it's under alpha and beta, it both equal to 0, and we have a good test for that. But for the other two, say alpha equal to 0, beta not equal to 0, they are not easy to deal with. And then we don't know the proportion of different compositions. So they sometimes will make the test for mediation can be very conservative. If you perform a multiple tests, so say if you do a genome-wide scan, everything is under the null, the p-value distribution will not be uniform. Actually, it will be very, very conservative. And that's a challenge of mediation hypothesis test.
Okay, thank you.
Thank you.
Okay, so I think we'll end this now. So I would like to thank Yen-Tsung for a very, I guess, deep presentation and thought-provoking presentation as well. And so I wish you all the best and happy holiday season for all of you. Bye-bye.
Thank you.